Okay, we continue our discussion of polynomial functions here. Here we have a root at -2, a multiplicity of 2, a root at 4, and a multiplicity of 1. So that means the exponents are 2 and 1 respectively for the roots -2 and 4 in factored form. So if my root is at -2, that means the factored form would be x plus 2, and if my root is at 4, my factored form would be at x minus 4. Since multiplicity 2, we square this, and multiplicity 1, we don't put an exponent there, it's just assumed to be 1. So there's our function f of x, and now I'm going to square x plus 2 squared, so therefore I'm going to write the x minus 4 in front. I just like having a linear factor in front. So this is x squared plus 4x plus 4. I may distribute the x. So I distribute the x, and I got these three terms here. Now I'm going to distribute the -4. Gives me -4x squared minus 16x minus 16. Notice that I line up like terms, and I do it vertically as opposed to one big long horizontal string. I do it up and down. So therefore my function is now x cubed, these two cancel out, minus 12x minus 16. Next example, I have -3 is a root and multiplicity of 2, and -1 and 2 are roots with multiplicity of 1. So therefore -3 is in factor form x plus 3 quantity squared, and then this is x plus 1, and this is x minus 2. I'm now going to multiply this, and I'll show you the result in a second. So I multiplied x plus 3, and I got x squared plus 6x plus 9, and I multiplied these two binomials, and I got that there now. So now I'm going to distribute this x squared over this trinomial. So notice I got these three terms here. Now I'm going to multiply 6x over these three terms here. Notice again that I line up like terms, and I write down after each multiplication, I shift it over one and go down one. So now I'm going to multiply this 9 through, so I get 9x squared minus 9x minus 18. I add up like terms. I get x cubed plus 5, excuse me, that's x to the 4th. X to the 4th plus 5x cubed. This is plus x squared minus 21x minus 18. Okay, next thing is a little theorem here that just says the number of mins and maxes that you can have in a polynomial function is always one less than the degree of the function. So an example would be if I have a quadratic, a parabola, the greatest number of turning points you can have for a quadratic is 1, because it's 1 less than the degree. Degree is 2. 1 less than that is 1, so the greatest number of turning points you can have is 1. And actually all parabolas only have 1 turning point. If I have a cubic or a third degree polynomial, the greatest number of mins or maxes you can have is 2, or number of turning points you can have in 2. In this case, there's no turning points, so the greatest number of you can have is 2, or you could have no turning points. Like in this case, you have no turning points. So in number 14, we have, if I was to multiply these two out, which would take me quite a long time, so it's not really worth doing, but the greatest number of turning points I can have would be 1 less than degree. So this is x cubed, and this is x squared, so that this is a 5th degree polynomial. So therefore, the greatest number of mins and maxes I can have is 4. So let's use the graphing calculator to find out these max and mins. And you will see that there's only one max and one min, so there's only 2 turning points, even though the greatest number of turning points I can have is 4. And notice I use the word most here because most just takes up less space, so I'm writing out lots of problems. So let's put that up on the graphing calculator. Okay, so here's my function in the graphing calculator. I usually start all my graphs out by doing zoom 6, the standard window. Hopefully I can see it. Notice here that it looks like there's a corner right here, but again, all polynomial functions are smooth and nice curves, so therefore there's no corner here. We just have to make our window a little bit better. Whenever I notice that my function is going straight up and down, I just need to move, in this case I need to move down because it looks like it does a little U thing right here. So I just move my y min down, so let's just choose an appropriate value for that. So I changed my y min down to -200. And my scale, y scale, those are the little tick marks that are along the x-axis. I'm just going to make that 50. I just don't like it, the x-axis to be all kind of blurred away. I like there to be little tick marks on the axes. So let's see what that looks like. Notice I still need to go down a little bit further. So 200 wasn't enough. Let's double that. And let's go down a little bit further. So notice that now my y min is at negative 600, and that should be enough. Correct. So it looks like we have a maximum right here, and we have a minimum over here. This maximum looks like it's actually an x-intercept, so let's go back to our function right here. Notice that x plus 5 is an even multiplicity, so therefore it touches the x-axis at negative 5, and in this case, it's actually a maximum, so let's just write that right in where we see maximum. We're going to put negative 5 comma 0, and we'll verify that using the graphing calculator. And then our min value is going to be this point right over here. So in order to find maximum, we go to second calc, we hit maximum, or you can just hit number 4. First thing I need to do is so if this is my maximum here, I need to have my left bound, that's saying where's your left bound, it needs to be to the left of where I think this max is. So it needs to be over here somewhere. So I'm just going to scroll over there just by hitting the right arrow. So I just pause this, you wouldn't have to watch me scroll around. So now I have my cursor to the left of where I think this max is, press enter. Let's scroll to the right. I'm now to the right of where I think the maximum is, so I press enter, and that's right bound, so I press enter again. It asks me to guess, and I'm okay with the guessing, so yes, press enter. And this is the calculator's way of saying this is negative 5. This is 4.99999, which is negative 5. And this is the calculator's way of saying there are 9 zeros, 0.9 zeros, and then 9. So that's the calculator's way of saying that that is 0. So you wouldn't want to write this down as an answer. You'd want to write down 0, and you want to write down negative 5, just like we did right there. So now we want to find the midpoint. So therefore we go to second calc, and we want to go to min, which is number 3. And we want to be to the left of where we think the minimum is. Well, the minimum's here, so we want to put the cursor there. And then we want to be the right of where the min is, so you just want to scroll over to the right. And press enter, and then we'd like you to guess. Yes, I would. And there's our min value, negative 2.19999 and negative 580.8499. So this is, so let's go back to the page here. It looks like this is just trying to say negative 2.2, and this is negative 580.84999. So I'm just going to write that in right now. So there's my minimum right there. Let's scroll down to the next problem here. Again, we have in this case, we have a 5th degree polynomial because it's a 4th degree right here, and this is a linear term. So therefore, this is a 5th degree polynomial. So the greatest number of turning points you can have would be 1 less than degree. So since it's a 5th degree, the greatest number of turning points we're going to have is 4. In this case, we actually only have 2. We have 1 max and 1 min. So let's take a look at that with the graphing calculator. So here's the function in the calculator. So I always start off with zoom 6, or the standard window. It looks like it's going down, but notice that it's not as steep as the previous one, so we're not going to go down as far as not going to have to go down as far as we did in the previous one. So let's go down to negative 100, and let's just change our y scale so we can see the little tick marks. I like tick marks. Assuming that's y max. Let's make this 10 and graph. And actually, it looks like we've gone a little bit too far down, so I'm just going to move it up a little bit. You don't really need to, though. So I just changed the y min to be negative 50. So it looks like that's where our min's going to be. It looks like there's going to be a maximum there right at the origin. If we look back at our function, there's the x-intercept. It is an even multiplicity, so therefore it does touch the x-axis at 0, 0. And since that's a maximum value, or a local maximum value, our max is going to be 0, 0, but we'll verify that with the graphing calculator. So we're going to do maximum, number 4, and we want to just be to the left of it, so press enter, and to the right of it, press enter, guess, yes. And again, this is the calculator's way of saying this is 0. So there are 5 zeros in front of this 29, and then there are 21 zeros in front of this 14. So this is the calculator's way of saying 0, 0. So you'd never want to write down an answer like this. You'd want to just write down 0, 0. So now let's find the min value. So let's go to min, which is number 3, and we want to be to the left of this one here. So I'm just going to pause the video so you don't have to. So now I'm to the left of where I think the minimum is. Let's press enter, and now I'm going to scroll to the right, which doesn't take quite as long. That's good enough. It doesn't need to be exact, and there's our min value, negative, looks like this is negative 3.2 and this is 41.94304. So let's just write that down on our, and there you go. So now we're looking at M behavior models. M behavior models are a function that has the same form as an original, a different function for very large values of x. So for very large positive and negative values of x, the two functions look essentially the same and have the same function values. So in this case, we have our original function is x squared times x minus 2, and our M behavior model I'm proposing is x cubed, because this is a third degree polynomial. So therefore, let's close that out, that's annoying. So therefore, this is a third degree polynomial, so therefore I'm going to say that this is the M behavior model of the function. So let's take a look at these two functions for very small values of x, and notice that they're not the same. And when I say M behavior, I mean very large values of x. So around the origin, these two are going to be different, but if we go out to very large values of x, these two are going to be pretty much the same or exactly the same. So let me just set that. So here's our two functions. Let's just make sure those are the same. X squared and x minus 2, there you go. And let's just start out at zoom standard, or for very small values of x. Notice that these two functions pretty much look different. I'm just going to make the screen a little bit bigger. So notice that clearly these two functions are much different. But I'm not saying that they're both the same for small values of x. I'm saying for very large values of x, or as x goes towards infinity, I'm saying that these two functions are going to look the same, or that x cubed is an M behavior model of y1, which is x squared times x minus 2. So let's just amend our window here. So notice that I made my y min be negative 100, my y max being 100. And then what I did here is, since essentially I'm looking at x cubed, I took my x value and cubed it. So this is really 10 squared to the third power, cubic to the third power. So that's 10 to the 6. So I put 6 zeros on here and 6 zeros here so I can see the two of them. And then we'll take a look, if you leave the x scale the way it is, how the y-axis just looks like a big black bar. And if I change the y-axis scale, it looks a little bit better. So for very large values of x, you're going to want to watch these two graphs. So let's actually turn them on. And I'm going to turn them on using the little ball with a tail. And you'll be able to see when one function is and the second one is being graphed. And you'll notice that they're almost exactly the same, but not quite. And then if I make the window even bigger, they'll look exactly the same. So watch the graph as it comes across the screen. So there's y1. And notice y2 is not quite exactly the same. Down in this region over here, they're a little different. And then notice right there, they're a little bit different. And that's only if I go out to negative 1,000. So let's go out a little bit further. So in this case, I'm going out to 10,000. And again, since I'm essentially just looking at x cubed, I took my y min and my max, I cubed 10 to the 4th. So if I cube 10 to the 4th, I get 10 to the 12th. So therefore, there are 12 zeros here. You just can't see them all, dot, dot, dot. And so I have negative 10 to the 12th and positive 10 to the 12th. I'm going to make my y scale, since this is 10 to the 12th, I'll make my y scale pretty big. Let's say 10 to the 6th. And hopefully you'll see some tick marks along the x-axis. And again, these two functions should look exactly the same because I'm out for very large values of x. So notice the little bouncing ball here. Hello? Why isn't that working? This little bouncing ball will show the difference between the functions, and they're pretty much you're not going to be able to tell the difference. So here's our first function, y1. And here comes y2 right on top of y1. Notice that there's no extra little rectangles, if you will, because that's just the best way TI knows how to graph, that they look exactly the same as you go out towards very large values of x. So you could only imagine, if I choose even larger values, that they're going to still look exactly the same. So therefore, again, we're trying to say that x cubed is an M behavior model of this function here. Let's look at it using the table. Let's go to table set. I don't care what table start and the changing table is, because I'm going to use the ask menu. So if yours is on auto and auto, just change your independent to be ask. That means you get to choose any value of x you want to plug in there. So now I'm at table set, so now I'm going to go to the table. And in this case, there's already some values here, so let's just delete those. And for very small values of x, you'll notice that these two values are different. So if we even go out to 5 and -5, you'll notice that the values are pretty different. But if you go for very large values of x, so let's go 10 to the 5th, they pretty much look like they're the same. I'm going to actually look at the function value. So this is this is y1 is 9.999 times 10 to the 14th, and this is actually just 10 to the 15th. So they're pretty close to being the same, and that was only for 10 to the 5th, it looks like. So therefore, if we go out to 10 to the 8th, so 10 to the 8th, if I cube it, I get something almost exact. See, this is 10 to the 24th, and this is 9.9999 times 10 to the 23rd, so it's almost exactly the same. So let's go out to 10 to the 10. Oops. And I think they'll be exactly the same. Yep, see, look, they're exactly the same. So for very large values of x, these two functions are essentially the same. So x cubed is an end behavior model of x squared times x minus 2. Let's look at another example here. This time we have a quartic, and what happens is, for very large values of x, all this stuff here has no value, because this overpowers these other three terms right here, especially this constant, this -3 has nothing to do. This x to the 4th overpowers that 3. So this is the x to the 4th is the end behavior model of this function here. And we'll just look at a graph of that to agree with it. Then we'll move on to 18 because the coefficient makes it a little bit different. Okay, so here are our two functions here. We have a quartic and the end behavior model x to the 4th. Let's take a look at Zoom standard. You notice that they're pretty much two different functions. The original function y1 does some funny stuff around the origin, and notice that the second one, as that gets drawn in, is much simpler. It just looks like a u. So for very small values of x or values around the origin, these two functions are pretty different, but I already set up a window that works. I'm going to go to the previous window I had, and for very large values of x, they're going to look exactly the same. So notice for very large values of x, we have a u, and here's our second one with the ball on it. It's being drawn right on top of it. It's exactly the same as the original one, so therefore we can say x to the 4th is an end behavior model of that quartic. I don't remember all the details of it. So there you go, exactly the same. So x to the 4th is an end behavior model of this function right here. Here's an interesting thing. The end behavior model of this polynomial, this 4th degree polynomial, has to include the coefficient, and we'll look at with the 5 and without the 5, and we'll notice that the 5 actually makes a difference, which is kind of interesting. So the end behavior model of this function wouldn't just be x to the 4th, it would be 5x to the 4th, and we'll look at that with the graphing calculator. Okay, so here are our two functions. The original function and the end behavior model. Let's just look at the two of them near the origin, and notice that they're drastically different. So here comes the first function, and then our second function is just the u. So they're not totally different, but the original function has this little funny stuff going on, and the end behavior model is just pretty much just the u. So again, I saved a window from previous, so pretty much the same window I used on the previous problem, and notice that that's my original function there, and then here comes the second function, and you can't even tell the difference. And just imagine that the window is quite large. I'll show you the window in a second as soon as the ball finishes bouncing across the screen. So notice for very large values of x, the two graphs look the same. And the interesting thing is, if you don't have the 5 there, the two functions actually do not look the same. So the end behavior model has to include the coefficient of the highest degree term. So here's the original function, and then look how much different it is without having the coefficient of 5. So the 5 is very important, and you can just imagine it keeps going. I just don't feel like watching this graphing anymore. So I'm actually going to pause the graph by pressing on, and notice that it pauses it for you. So therefore, this is the end behavior model of this large quartic right here. So you can imagine that -2x cubed would be the end behavior model of this cubic right here. And that wraps up end behavior models and turning points.